Okay, let's start up. I can't say anything. We're going to be talking about the first chapter of first section of chapter 15. So what we're going to do is this. We are starting a discussion of galaxies. And the way we're going to approach that is the same way that we approach talking about stars. We're going to start the discussion by talking about our own galaxy. And we're going to learn a lot of characteristics about our own galaxy that applies to other galaxies and some things that just apply to the Milky Way. So that's what chapter 15 is going to be devoted to, is talking about the Milky Way galaxy. So does anybody happen to live in a remote enough area where you can see the Milky Way in the sky? You can, yeah. When I went to Flagstaff to visit a friend of mine, there was like somewhere in like Ludlow, which is just nowhere. I just stopped and looked up and saw it. Yeah, Rosamond's okay. California City's good. Like LA, people say they see it out there. Any what? No? Oh, some people can. Yeah. If you get in a remote enough area, but here in Lancaster, we can't see this. But the appearance of it sort of looks like distant clouds in space. Doesn't really appear like much. And throughout most of history, humanity could see this object up in the sky, but really nothing was known about it until Galileo. He was the first person to look at this and realize that it's not clouds up in the sky, it's not clouds in space, it's actually a collection of stars. Okay. It's a disc-shaped collection of stars that we are a part of. If you take some of the, if you look down on the image here, there is some bright stuff. I mean, you have this band of sort of dark nebula and some emission that's here. The dark nebula that's here is all the dust and gas that exists in our galaxy. And as you get sort of away from that, you'll see that there's sort of some bright stuff, and it kind of diminishes as you get further away from that disk. Those are all stars. There's not like reflection off gas here. All that light is just pinpoints of light. When Galileo looked at this through his telescope, he realized that the nebula that we see here is not really a nebula. It's more like a disk. It's more like pinpoints of light, millions of pinpoints of light. So we know today that that's the structure of it. And nothing was really done after Galileo to look at the structure until we get to this guy here, William Herschel. William Herschel did a lot of things. He was kind of the prominent astronomer of the 18th century. He discovered Uranus. He's the guy who named Planetary Nebula, among other things. And he did a lot of really important investigations in all areas of astronomy. And one of the things he did was to look at the nature of the Milky Way galaxy. And he did some studies, and he deduced that the sun must be at the center of the Milky Way galaxy, which at the time also implied that the sun is at the center of the universe, because at this point, the idea of a galaxy and the universe being different didn't exist. At this point, we don't know that other galaxies exist. In fact, at this point, parallax stars weren't even discovered, and Uranus was recently discovered. Neptune wasn't known at this point. So even the distinction between solar system and galaxy wasn't well developed. Now let me try to explain why he came to this conclusion. What he did was this, is he looked all around the disk, and he attempted to count the number of stars in each different section of this disk-shaped structure. And his logic went like this. If we count stars in the different regions of the structure, that if there were, say, more of the Milky Way galaxy on one side of our solar system, we would count more stars than on the other side. This would be equivalent of you're in a big crowd of people and you want to figure out where you are in that crowd. Okay? If you look around you and you see sort of equal numbers of people all around you, then you're at the center. But if you're off to one side, there's going to be one side where there's going to be a lot more people, and on another side there's not that many. That's the logic he's using here. So as he does his counts, he's discovering that there's basically equal numbers of stars all the way around. So this is how he deduced that we are at the center. Now this is not true. We're not at the center of our galaxy or the universe, and but he didn't really make a mistake on what he did. He missed something. There was something that wasn't known. That wasn't going to be known for another 150 years or so. But this is sort of the first step in trying to discover the nature of this. What he didn't realize is that the disk of the galaxy is filled with dust and gas. And you might remember when we talked from star formation that one of the effects of that is to prevent us from seeing very far away. There's interstellar reddening and there's extinction. So as he looks into the disk, you can't see very far. So this is like the crowd is in a fog, and it only allows you to see a few people on either sides of you. And so if you didn't know the fog existed, you'd think, oh, this is a small crowd, and I'm in the middle of it. You're only in the middle of what you can see. He didn't realize that there's essentially a fog that prevents you from seeing very far. And if you clear the fog away, you can see much, much further away. And so looking into the disk as an attempt to study the whole galaxy is a bad idea. And this was something that wasn't really known until the 1930s, and this prevented astronomers from really discovering the extent of our galaxy. So anyway, that was believed for another about 150 years or so. So what changes is around the 1910s or so, there was a new way to get distances in astronomy. Parallax was established beforehand. I think it was first used around the 1850s. And right up until the 1910s, the only way we got distances of things were parallaxes. And parallaxes, you remember, not very, it's not good for faraway distances. But a really important discovery was made with a class of stars called Cepheid variables. Cepheid variables are a type of giant star that pulsate. They get larger, they get smaller. It's a stage that giant stars go through. In fact, there's a whole thing with giant stars that we didn't get into. You don't want to get into. It's long and very tedious. But anyway, some giant stars go through this phase where they kind of heat. They get larger, smaller, larger, and smaller. So because their size changes, the luminosity is going to change. And so this picture on the right here is a Hubble image of a Cepheid in a different galaxy, actually. And what we can do is we watch that Cepheid, and we can see it get brighter and fainter, brighter and fainter. We can create what you see on the left here, which is a light curve. You watch the object periodically go through maximum and minimum brightnesses. And you look for what we call the period of it. The period is how long it takes to go through one full cycle of it. So in this graph here, from a maximum down to a minimum up to a maximum looks like it's about 50 days. So we would say that this Cepheid variable has a period of 50 days. Okay, and there's a lot of giants that are like this. Now why is this important? It's because this astronomer here, her name is Henrietta Leavitt. She published a paper in 1912 where she announced the discovery between a relationship between the period of these objects and their luminosities. Okay, it was between period and luminosity, and there was a linear relationship for most of these objects. Now, there's several objects on the chart over here. What we're interested in mostly are these type 1 Cepheids at the top. There's a 1-to-1 correlation with period and luminosity. The longer the period is, the more luminous the objects are. And the reason why she was able to do this is because there are some nearby Cepheids that we have parallaxes to. So we can get their luminosities and we compare them to what their periods are, and then she made this discovery. This is a huge deal because it allowed distances to be determined that are orders of magnitude larger than what currently exists. And so this, let me explain the idea behind it. Okay? The idea behind this is based on the brightness law. Okay, so the brightness law is the flux of a star is related to luminosity divided by distance squared. And the way we used this relationship previously was you could always see the star, that's its flux. And then we use parallax to determine the distance, and then you work out the luminosity. This method here allows you to go backwards, basically. These are objects that have a known luminosity. If you watch the object, you just determine how long it takes to go through a full cycle, that's its period, some number of days. Okay, on here you can see anywhere between 10 to up to 100 days, or how these objects are. This relationship allows you to determine what the luminosity is. And since you can see the object, the difference between the two is going to be the distance. So this is using the brightness law by going backwards in it. And this is a method that we're going to see a lot for galaxies. It's called a standard candle method. These are objects where we know the luminosity, and so if we can see the objects, we work backwards through the brightness law, and we get their distances. And this is a really big deal because these are giant stars, and giant stars are really bright, and you can see giant stars that are very far away. That picture we had at Hubble, that picture was of a star in another galaxy, which that's pretty far away. So so this method is really great because you can see things that are really far away. The only downside to this method is you get a distance to a single star, which is nice, but you want to associate it with something else and to get the distance to a bunch of other things. But anyway, she developed this method, and this is a big method that was used. And so as a result of this, within about 100 years, there was a flood of discoveries made in astronomy, mostly related to galactic astronomy. In fact, within about 100 years, we determined the nature of our galaxy, the size of it, the anatomy of it, and we discovered the existence of other galaxies, all basically because of this work. Yeah?
Didn't they already have an idea of how far something was because of the telescopes that they use? Don't telescopes let them know how far they're seeing out?
Well, without parallax, the only way you're going to really know a distance is through this brightness law. And so they have really crude estimates because they have to make some pretty crazy assumptions about the luminosity of an object. So the idea is this. You say, okay, well, here's a G star. That's our sun. There's this other G star they found that's really, really far away. And so if we assume they're the same brightness, which may not be right at all, then the difference would be based on their distance there. There's two problems with that. One, you make an assumption that it's exactly like the sun, and we know that that's mostly true, but there are some differences. Also, you're assuming that nothing between you and that star is affecting the light of the star. And they knew that there was always some effect of the interstellar medium maybe blocking some of the light. So you can do it. It's really crude, but it's something you can do, yeah. But this is a much more precise method. And that's why it was so good. All right. So now, so with this method here, you have to find these objects, okay? And the best place to find giant stars are going to be places where stars are dying because giant stars are dying. And so a good place to look are these. These are globular clusters. We mentioned them back when we talked about, whenever we talked about that stuff, starburst, star death. But globular clusters there's about 200 of them, all spread out through our galaxy. They're in the disk, they're in the halo, they're kind of all over the place. And these are really old, and they contain a lot of giant stars. And so it's very easy to find Cepheid variables in these things. And so if you find Cepheid variables, you associate it with a cluster, you get the distance to the Cepheid variable, you effectively have the distance to the cluster. And so this gentleman right here on the right, his name is Harlow Shapley. He set out a pretty big observation routine where he decided to look at about half of the globular clusters that are known, and he searched for Cepheid variables. So this is basically what this requires is go out every night, take pictures of globular clusters, just for weeks and months to take pictures of these things and very carefully study the pictures and look for stars that are changing brightness. This is actually really challenging to do, and imagine you have to have a lot of patience to do this. Once you do this for every one of these clusters, there's 93 of them that he used. You look for the changes, you isolate those objects, and you start to determine what their periods are. And then you use Henrietta Leavitt's luminosity, period luminosity relationship, and the brightness law, and then you get their distances. So this took years, actually. This is a very difficult set of observations, yeah.
Okay, so which luminosity do they use for the equation? Do they use luminosity when it's at its highest brightness?
Right. Good point. Yeah, it changes luminosity, so this is describing it at its max. Yeah. All right, so it just took many years, but he was able to identify many Cepheid variables in all 93 of these things. He worked out two things: the distances to the globular clusters, and then he created a map showing where they're all distributed in the sky. And this is a reproduction of his data. This is just, it looked basically like this, but it was all old-timey and stuff, and so I'm making it look nicer. So all of the dark circles here in the figure are all open clusters, and that's just indicating where the disk of the galaxy is. Okay, so this picture here, the way it's organized, it's with galactic latitude and longitude. So if we actually go back to this picture here, this is like the same picture. Okay, galactic latitude is how far above or below you are from the disk, and longitude is like left or right. So that's basically what the coordinates are here. So we can see pretty clearly where the disk is. And then all the open circles, those are all locations where the globular clusters are. Okay, we're not talking about distance here, we're just talking about the globular cluster locations. Okay. And so there's something kind of really interesting about this. First of all, there is a place where they're all bunched up. Right? You see where that is? Right in the middle, which we now call the middle. We didn't call it the middle before, but that's the middle. And that is in the direction of the constellation of Sagittarius. And so they're all bunched up there. Now, what Shapley did was what Herschel was trying to do. He's trying to count things and trying to figure out if there's more on one side than the other side. The fact that these are all clustered right here in the middle is indicating where the center of the galaxy is located. Okay? Most of the globular clusters are found near the center. They're all found off the same side. Now, if you look 90 degrees on either sides of that point, that's where you find most of the globular clusters. If you go beyond that, there's hardly any. There's like 4 or 5 or 6 or something like that, which means there's one half of the sky that has almost all of the globular clusters, and the other half has barely any. So this is exactly what Herschel is trying to do. Okay? That direction is the direction towards the center of the galaxy, and the reason why this worked is because these objects are not in the disk of the galaxy. Some are, but a lot of them are above or below the disk. So you're not looking into a bunch of dust and gas. Okay, you're not looking into the fog. So it allows you to see much further away. And so this is, like I said, exactly what Herschel's trying to do, but they're able to figure it out. And by the way, this picture here is basically the only picture we have of our galaxy. The only one, the whole thing. Yeah.
So where like the bright, like white yellow pictures, that's where all the open globular clusters are?
Yeah, all along the disk in the middle here. That's where that band is. That's where most of the star formation takes place. You can see where the bulge is inside the center here. Yeah, I put that little dot there on the right just to indicate where we would be if you know we saw a side-to-side picture, but we're sort of in the galaxy. This is like the best picture we can get, an edge-on picture. I mean, this is a selfie, pretty much. So it's a whole sky image that's been mapped to a rectangle. It's like taking the whole globe and just putting it in a rectangle. Same idea. It's the way the projection's done. But this is the best picture, pretty much the only picture we can ever get, one from the perspective of being inside of the galaxy. So anyway, that's it. All right. So first thing Shapley did, big deal, was figured out where the center is. The second thing he did is you take all of these distances here and you create an average. You add them all up and divide by how many they are, and that average will give you the average distance to the center. And so from that and some other things, Shapley was able to create a picture like this. This is sort of the first time we're able to put together what the structure of our galaxy is probably like. And so we know the center is towards the constellation of Sagittarius. We are able to determine that we're approximately 8 to 9 kiloparsecs away from the center. We see that our galaxy has a disk structure, but it has two other structures as well. There's a bulge that occurs at the nucleus. The thickness of this disk is very thin. It's about, the thickness is about a kiloparsec, whereas the whole length across is about 50 kiloparsecs. So very thin, okay, about 2% of the diameter of it. And then we also have a halo that surrounds the disk. That's where most of the globular clusters are formed. So we have basically three parts to our galaxy. We have the disk, the halo, and the center we call galactic nucleus. Okay. All right. So this was the first time we were able to put this together. And again, at this point, we don't know of other galaxies. We think this is it, our galaxy, this is our universe, we're shaped like this. Okay? Any questions about this? Yeah.
So, is it contracting, or is it
It's just chilling out, just spins. One spin takes about, depending on where you are, it takes about 250 million years. But that's we're not really expanding, contracted. We live in a cluster with about 30 other galaxies. There's like us, and we're surrounded by 10 or 12 different things. They all kind of swarm us. We move as a big group. And there's another group which just has Andromeda and Triangulum. They're big spiral galaxies. They have a bunch of little grunty things around it. We just kind of move as this big group throughout the universe. That's what we do. Yeah.
So, are we able to see the halo in that photo that we have of our?
No, you don't really see it, which is a good point, actually. So when you look at a picture of a galaxy, what you generally see is you see the dust and the gas. You see dark nebula in contrast with a bunch of bright nebula. The stars are really small pinpoints of light, and they don't really make up much of a structure. So the halo doesn't have dust and gas in it. It's almost gone. And all it has is just a bunch of really old stars, which aren't very bright. So making out the halo of a galaxy is really hard. We can't do that for ours, and only for a few galaxies can we actually make out some kind of halo.
But he just knew that we had a halo because it's a property of the galaxy type of thing?
No, he knew we had a halo because a lot of globular clusters are in there. So the halo itself is not like this continuous structure. There's just these, like you see here, these clusters are all kind of strewn about the center there. And from their motion, you can see that they're kind of swarming the center. So that's how we're creating the halo.
Oh, because I think of a halo as use like a single line, but it's really
No, halo is like a sphere. Yeah, I know what you mean. We say halo. Halo represents like a spherical glow, basically, to the galaxy. I could show you, I suppose, let me actually show you a picture. Where would that be? Why am I not I'm losing my mind here? Okay, hold on. No, I have a picture, but I just can't remember where it is. This is galaxy. Oh, that's not right. This galaxy I'm going to show you here is called the Sombrero Galaxy because it's supposed to have a sombrero. But anyway, this galaxy has a pretty significant halo. Okay. No real structure to it. It just kind of glows because it doesn't really have dust and gas. It just has like lots and lots of somewhat faint stars that create that all the pinpoints of light create this hazy structure to it. That's the idea. That's probably the best picture I could show you of a halo. Anyway, all right. Any other questions about that structure? Here's another picture of it. Well, these are sort of two different views. And the view on the bottom is a view that we can get. It's an edge-on view. Sean. This is an edge-on view, is the bottom picture there. And that's the picture that we can get of our galaxy. This is what we call a face-on view. A face-on view is where it's tilted to our line of sight, so we actually can see the spiral structure. And any other galaxy we look like has a combination of being edge-on and face-on, or something in between. So the nice thing about an edge-on galaxy is you see the thinness of the disk. If there's any halo structure that can be made out, you can make it out. You can see the sort of the galactic nucleus a little bit better. You cannot see any halo structure at all when you get a face-on picture, but you get the spiral structure. It looks a lot nicer. Okay. Right, so this is a face-on picture. This is the Whirlpool galaxy somewhat nearby. Lots of spiral structure to see. This is sort of our prototypical spiral galaxy to look at. It's big, it's nearby, it's pretty. It's in pretty much every calendar that's ever been made. It has astronomy images in it. So, and it's actually odd because this is like your sort of prototypical spiral galaxy the way people envision it, but this is not normal. This structure is caused by another galaxy tearing this one apart. And it's kind of like, I don't know, it's kind of like you have wrinkly skin, but your face is being ripped apart, and like that one moment where like it's stretched out and all the wrinkles are gone and you look fine. You know what I mean? It's that. Because this probably had a lot of irregularities, but it's actually being pulled apart, and as it's being pulled apart, it's smoothing out the irregularities. So it actually looks kind of symmetric and nice. We call these grand design spirals. There's usually something causing it, and there's a galaxy nearby that's ripping it apart. So that's the idea here. All right. So the last in this historical stuff after Shapley is Edwin Hubble. So at this point, we've established what our galaxy's like. And the only other mystery now about our galaxy is that we have these really large structures that they just call them mysterious nebula, that were found basically all around our galaxy. There wasn't really known what the nature of these things were. And for several years, there were these debates as to whether they were part of our galaxy or maybe beyond, if they were star formation regions or something different. And Edwin Hubble was able to sort of settle the debate. And the reason he was able to do it is because he worked here at Mount Wilson, which in the 20s had one of the largest telescopes, optical, in the world. And so the most amount of detail could be seen with that. And so when he looked at a lot of this mysterious nebula, what he discovered, sort of in the spirit of Galileo, was that all the nebula were pinpoints of light. And they were actually galaxies themselves. They called them initially island universes. This is the closest one to us. It's called Andromeda. It was called the Andromeda Nebula. Now we call it the Andromeda Galaxy. So he realized that they had a lot of similarities to how our galaxy looked. And then he looked very carefully to look for Cepheid variables. He found Cepheid variables, and he worked out the distances to them based on Henrietta Leavitt's work, and he got distances that were over 600 kiloparsecs. Okay, our galaxy's diameter, we estimate, is about 50 kiloparsecs. So these were distances that were, an order of magnitude larger than the size of our galaxy. So these were clearly outside of our galaxy, their own separate systems of stars, and he discovered the first of these things. This is like in the mid-20s is when this was done. And at this point, we discover that not only are we not the center of our own galaxy, but there's more than one galaxy, there's tons of galaxies. And so he spent the next 10 or 15 years discovering tons of other galaxies and learning their properties. So I don't know at what point we started calling them galaxies, but they were called island universes, which is, I think, sounds better, but whatever. Galaxy it is. Okay, yeah.
You know how that Whirlpool galaxy is like, it's being like tugged on by another galaxy?
Yeah.
Is that galaxy like, the one that's tugging on it, is it like less than like 500 kiloparsecs close to it?
No, it's pretty close. In fact, this was the first galaxy discovered, but it's not the closest. It's the closest galaxy of significant size. There are 10 to 12 other galaxies that are smaller and closer to us, but we had no idea they were galaxies until much later on. We didn't even see a lot of these objects. In fact, the large and small Magellanic Clouds, which are in the southern hemisphere, you can see them with the naked eye. We didn't know they were galaxies until basically this time here, and they discovered they were much closer. Those objects are only about 100, well, not even 100 kiloparsecs. They're more like, no, they're really close. They're close to about 50. Yeah, they're right. They're right next to us. They're And there are galaxies that are closer. There are galaxies, we know of one galaxy on the other side of our galaxy that overlaps with us. It's actually part of our galaxy. So that's pretty common. There's one thing you're going to see about galaxies is the environment of galaxies is really crowded. It's not like stars. Stars have these huge spaces between them. Galaxies don't. There's a lot of clusters of galaxies that have galaxies overlapping each other. And collisions between galaxies are really common as well. Okay. So I'm going to spend a little bit of time talking about the motion of things in the galaxy. So there's something really weird about our galaxy. Not really our galaxy, something really weird about spiral galaxies in general. And that's this, that there are two major components to spiral galaxies. There's what we call the disk, and there's what we call the halo. Okay. So major distinctions for spirals is disk and halo structures. Okay. We live in the disk. Okay? And the stars in the disk have very consistent properties. The stars in the disk stay in the disk. As they orbit the galaxy, they orbit in things that are very close to circles. And they all orbit the same direction. They don't incline very much. And they all move as a kind of a big group around. So it's kind of like the solar system. Everything kind of goes the same direction, not big inclinations. The disk is completely analogous to like a solar system. But the halo, it shares the same center, but the stars are radically different. So they have random inclinations. They don't stay in the disk. They have highly elliptical orbits. They can approach, as they orbit, they actually go in random directions. Some go prograde, some go retrograde. I mean, it's like a swarm of stars, just kind of randomly strewn about, moving in strange elliptical paths. And so two totally different regions that share the same center. It's like actually having two different galaxies right on top of each other that share the same center, because the stars that make up this are not exactly the same kind of stars that make up this. All the stuff we talked about in the last few chapters, all those rules mostly apply to disk stars. These are slightly different, actually. There's the same kind of spectral types and everything, and the HR diagram applies. But these are extremely old stars, whereas these are relatively newer stars. All right, so we're going to focus on the disk. The disk is not a rigid object. Okay. When stars orbit in the disk, they can move at different periods. Okay. And in fact, we say the galaxy has a differential rotation to it. So some parts move faster, some parts move slower. The Earth's a rigid object. Everything takes the same amount of time to go around once. The sun is not a rigid object. The equator spins faster than the poles. So it's kind of like this. So with the way it works in the galaxy, the closer you are, generally, you're faster. Not necessarily, but generally you're faster. The further you're away, generally you're slower. Okay. So we're going to look at the sun in particular. The sun goes about the galactic center at a speed of about 220 kilometers per second. That's how fast. So that's like 100 and, what would that be like? It'd be like 140, 150 miles per second. That's what we're doing. The solar system is doing this. The solar system is moving at about 140, 150 miles per second. In fact, I got a video of that. I got a great video of that. No, I don't. Well, yeah, I do. I'll look for it. Okay. Let's see. Oh, listen to that guy. All right. So let's see here. Solar system helix. Is that going to work? Okay, so this is. I think this is actually. Okay, I don't know. This guy's named DJ Sadu. I don't know who that is, but this is a pretty good representation. Oh, it was an ad. Okay, this is a pretty good representation. Well, it's for that. Okay, so this is a representation of what our solar system is like as it moves about through the galaxy. So this is not a sun-centered perspective. This is like we're kind of moving with the galaxy. This is way too loud. Okay, so that's a sun-centered perspective. All the planets are going around the sun. It's not incorrect, actually. It's a matter of perspective, but. So like I said, that's about 140, 150 miles per second. And so if you don't have sun-centered perspective, you have this. So the sun orbits the galaxy in basically a circle, and all the planets get kind of tugged along. So this would be a sort of a good representation of what the solar system probably looks. That's what all solar systems really look like from the perspective of the center of the galaxy. Okay, they all have this like helical motion to it. Yeah, we're doing all kinds of things. We are orbiting the sun orbits the galaxy orbits center point sort of in our cluster, and then our cluster orbits something else.
So, like, all that stuff, like, that's like past, like, Neptune, is also moving just like that?
Yes. Now, the reason why this seems strange is this is just Newton's first law, though. I mean, the sun's not really dragging everything along. Everything is already moving that way. So it's not, it seems like something's dragging stuff. It's not really dragging stuff along. It's just simple Newton's first law stuff. Yes, we are.
That doesn't seem right either, though, because you said that the disks of the planets orbit the same way as the disk of galaxies. There's not much flow.
Oh, no, not in terms of, no. So what I mean is that the shape of the disk is a disk, and the shape of the solar system's disk is a disk. But they are tilted. In fact, the actual tilt's around 60 degrees. So if you imagine the galaxy being the flat thing, this should be at a 60-degree angle as it goes around. Yeah. And that's random. Like every galaxy, every solar system has their own random inclination to that. Now, there's no pattern to that. Yes?
At the galactic center, is there, like a force that's, like, you know, is it, like, such a big, like, is there, like, a big object that's causing everything to orbit? Where it's doing all
No. Actually, you know what? I'm not going to answer your question.
Oh, man.
Because I'm about to answer your question.
Oh, okay.
Sorry, that's why. Okay, so let me answer your question by not answer your question by I don't know what I'm saying. Okay, anyway. So yeah, that's how we go around. 220 kilometers per second. If you we like I said, we're about 8 to 9 kiloparsecs out from the center. It's closer to 9. And you actually work out, okay, how long would it take for an object moving 220 kilometers per second to cover a circle, the circumference of a circle that has a radius of around 9 kiloparsecs. So you get this number here. Okay, that's about 250 million years. That's how long it takes for our solar system to complete one full orbit. And so based on how long the sun's been around, we're talking about something like maybe 18 or 19 trips around.
Oh, we're so young.
You were very young. Yes, exactly. So, now, why do we do this? Okay. Well, I'm going to draw a circle here that represents basically our orbit. Everything that's located in that center, every little bit of mass, is responsible for moving us in the circle. Okay? In fact, everything that's in that circle gravitationally tugs on us. It's not one thing at the center. In fact, it's all the mass that's located in the circle. all the mass that's outside the circle has no influence over us, actually. Because when you're outside the circle, any tug from a piece of mass would have an opposing tug on the other side, assuming things are basically distributed evenly here, which they kind of are. So that's something you're just going to have to believe. Okay? Yeah, it's a whole physics thing, and we can go into it if you take a physics class sometime, but not today. Okay? So everything inside the circle controls our orbit, outside does not. Furthermore, it doesn't matter how you distribute the stuff in the middle. It could be spread out in a disk like this, or it could all be stuck at the center. Doesn't really matter. Same thing with the sun. The sun's a sphere, we orbit the same way we do. If it turned into a cube, everything's fine. If it broke into 100 cubes, everything's fine. As long as it's basically symmetric, we're okay. Okay. So how you distribute the mass really doesn't matter. So what we're going to do here is we're going to treat this system as a binary system. Our sun and the Milky Way galaxy is going to be a binary star system. Okay. That's what we're going to do. And so if you treat it as a binary star system, you can use Kepler's law, the Newton's Kepler's law. We know the period, 240 million years. We know the distance. Okay, the distance is being close to 9 kiloparsecs. You got to convert that into AU. Okay, but when you put it into Kepler's third law for masses, you get 200 billion solar masses. So obviously the sun is 1. That means all of the mass that's located in the circle amounts to about 200 billion solar masses, which would be mass that's due to mostly stars, but a bunch of dust and gas as well. Okay. Now you can play around with this, and you can do different distances. You can choose one that's closer, one that's further away. You actually can create different, profiles of things that are closer or further away. The next question you sort of ask yourself after this is, well, how many stars is that? Well, okay. If every star is like the sun, there would be 200 billion stars. But is that true? No. The average star has a lower mass. So in terms of numbers, there probably are higher numbers than 200 billion. What we say, though, it's pretty safe to say that order of magnitude, we have hundreds of billions of stars in our galaxy. And it's based on many things, this being one of them. Okay, it's kind of you have to assume that our sun is like in a binary system, and this is how we determine the mass. Okay. Now this thing here, this is a rotation curve of our galaxy. This is like an HR diagram for galaxies. This is on the same level of that. And so what we just did by choosing the sun and working out its numbers, you can create a graph like this where you basically choose objects at all different distances and you work out how fast they go. And so this is the picture we get for our galaxy here. And you can take any particular star with these numbers and you can do Kepler's third law, okay, with them and figure out different mass estimates here. So let me explain how this looks here. When you start at the center, things don't go too fast, but they shoot up pretty quickly because there's a lot of mass in the center of the galaxy. Then it starts to drop off, which you would expect because that's how gravity works. We get a little bump here because we're starting to include a lot of the spiral arms, which have a higher concentration of mass. As we get out beyond the sun, we expect the behavior of stars to follow this blue dashed line. We call that Keplerian motion. That's just if things follow Kepler's laws, which they're supposed to, then the further you get away, you have less and less mass. Now the inverse square law for gravity should be taken hold. And you expect things to get really slow as you get far away. Well, there's a very weird thing that was discovered starting in the 30s and since then, that if you get really far away, we don't actually find stars that are down here. You never find stars that are growing slow. In fact, we find stars that are going extremely fast, and in most cases, they're going faster than any of the speeds further in. And this is really weird. Because, our sun, the reason we have this speed is due to all the mass that's inside there. And so, presumably, the speed of the stars that are way out here on the edges of our galaxy would be due to the same thing. All right, so when we do it with the sun, like I said, being about 8 to 9 kiloparsecs away, we get 200 billion solar masses. If we decide to use one of those halo stars I mean, one of the stars that are really far out on the edge of the galaxy, way out there. And you do Kepler's law, you get 1 trillion solar masses. You get 5 times more mass. So by going out a little bit farther out and choosing a star on the edge, you would expect the mass to go up a little bit. Because there's just a little bit more mass out there. But instead, we get 5 times the amount of mass. And we don't see that. I mean, right here, that's where our sun is, that dot. And we say that if we go all the way out to the edge and do the same thing, then all of a sudden you have 5 times the amount of mass. And that's really weird. What?
But the math works.
Well, okay, so the interpretation at the time was there's a lot of mass out there, we can't see it. We wonder what it is. Well, we call this dark matter today. Initially, it was believed that there is a lot of extra mass out there, perhaps in the form of black holes, white dwarfs, maybe brown dwarfs, other things that just have a very low luminosity. But it's very hard to fathom that there would be 5 times as much of that stuff, and it happens to only be on the outside of the galaxy, not inward. Some galaxies, every single galaxy has this appearance, by the way. This rotation curve that I'm showing you here, every galaxy has the exact same kind of rotation curve. It has some squiggly stuff at the front, and when you get very far away, it flattens out and it gets very fast. Every galaxy shows this.
Does that mean for the velocity constant does black matter have a rate of expansion?
We don't know. We don't know if it's affected by expansion or not. We don't know. Well, okay, so what are the interpretations? So like I said, at the time it was believed that it was matter that wasn't very luminous. Okay, but when you look at other rotation curves, there are some galaxies that have 100 times the amount of dark matter compared to visible matter. And that's, you can't, it's really hard to believe that somehow there would be 100 times more black holes, white, all this stuff that doesn't release a lot of light. And there's actually a lot of other ways you would detect that stuff as well. We don't see that. So we believe we've eliminated all of the expected low luminosity sources of this stuff. And now today, which is about 80 years after this was initially discovered, there are 2 potential explanations for this that astronomers and physicists are currently working on. One is this. Here's what we know about this stuff. It has a gravitational influence on things, so it has mass, probably. But it doesn't interact with light. So it's not atoms. It's not protons and electrons. And that's really bad because, everything we do here depends on light. We have to get light from stuff. And it's actually really not very surprising that there's a lot of stuff out there that doesn't interact with light. I mean, that's not unreasonable to believe, actually. So one explanation of dark matter that was popular in sort of the last few decades was dark matter represents some exotic new kind of matter that we have yet to detect. It's not stuff you find on a periodic table. It's not electrons, not protons, doesn't contain any of that stuff. We don't know what it is. We think it's probably really massive stuff that works by the weak nuclear force. Just doesn't interact with protons and neutrons and electrons. Again, not a surprise. There should definitely be, it's not surprising to believe that there's matter that doesn't interact electromagnetically. And we depend on electromagnetic things. So there's been a lot of attempts to search for this stuff, and we haven't come up with anything. Since that has not been successful, there's been, in the last decade or so, a alternative explanation that says that dark matter isn't matter. Dark matter is a misunderstanding of gravity. That the law of gravity that inverse square law, well, actually, Einstein discovered the inverse square law is not very accurate, actually. And so he created his own theory of gravity called general relativity. He did that in the 1910s. So we use that now. You can get an inverse square law out of that stuff, but so at least recently we have reformulated how gravity works. Well, people believe now that maybe we still don't get gravity. That maybe at faraway distances, gravity is not an inverse square law. Maybe it's a linear law or something. Actually, gravity increases to some extent. So that's the two leading theories, is that this mysterious matter doesn't interact with light, has mass, and it, for some reason only hangs out on the edge of the galaxy. Okay? It only exists in the halo. It doesn't exist in the disk, doesn't exist very close to the center. Or the other explanation is gravity's wrong, and we have to come up with a new law of gravity. And that's where we stand right now with dark matter. And this is not the only way we see dark matter. We're going to get into other galaxies in the next couple weeks or so. And dark matter kind of shows up in a lot of other ways. And so this is the first way we've seen it, though. Any questions about this idea? Yes.
So, okay, we can go to the next slide.
After this?
Yeah. Oh, whoops, okay, go.
Okay.
Go back. Okay, so this whole idea all came about because of the fact that the stars didn't fall that blue line.
Okay, yeah. This all comes from a single observation. The observation is that at faraway distances, stars don't travel slower, they travel faster. You know, the way the solar system works, the further you go away, slower things are. That makes sense. This is an attempt to explain this observation. Why do stars go really fast when they're far away from the center of galaxies? That's the question. That's the question we want to ultimately answer. Not what dark matter is. That's not really the question. The question is ultimately, why does this happen? Why do stars travel really fast when they're far away from the centers of galaxies? I mean, the two explanations are, well, there's a lot of mass out there. There's a ton of mass out there. It's dark. We can't see it, and that's what speeds things up. Because there's all this extra mass that exists out there. Or we just got gravity wrong when you're far away from things. But the question really boils down to that. Why do stars go that fast when they're far away? Yeah, Jacqueline? Well, we interpret, yes, we do see different, I mean, the rotation curves have the same basic appearance where things are always fast farther away and they kind of stay flat. Now, any differences we've simply attributed to the fact that some galaxies have more dark matter and some have less. That could be wrong. Well, what we do is this. We create something called a mass-to-light ratio. So we look at how much light comes from a galaxy, and since we know how stars emit light, we have a pretty good idea of how much mass should exist based on how much light we get. And so if there's no dark matter, every galaxy should have a mass-to-light ratio of 1, meaning all the light is associated with all the mass. But our galaxy, for example, has a mass-to-light ratio of 5. 20% of it, of the mass, can be accounted for by the light, but the other 80% is not. So, and some galaxies have really different ones. We have a 5. I've seen galaxies that have a mass-to-light ratio of 100. So, the interpretation is for some reason there's just a lot more in that one. But there could be other explanations, of course. That's the idea.
Are stars in the higher dark matter mass solar systems really travel faster? They accelerate faster?
Relatively speaking, yes. There's actually a couple things about those. One, relatively speaking, yes, they travel faster. Now, it also depends on the size and the distances. But another thing that we find is that dark matter galaxies with a high concentration of dark matter tend to not be spirals. They tend to be giant elliptical galaxies, which we'll get into next time. But an elliptical galaxy is just like a spiral without a spiral. It's just the halo. And the ones that have the higher percentage of that tend to be giant elliptical galaxies with no disks. And what explanation for that is, as we're going to see later, we know that you can form ellipticals when, in some cases, you can form ellipticals when spirals collide and merge together. So it's possible that many galaxies collided and sort of added up all of their dark matter stuff. Yeah, this is like, we have a lot of observations and we've had no observational evidence of anything at all. And this is kind of silly in a way because when you combine dark energy, which we'll talk about even later, and dark matter, that counts apparently for 96% of our galaxy, of our universe. Everything we've talked about, everything we will talk about is about 4% of our universe. So thank you for taking me seriously, because I'm only describing 4% of what we know. It's kind of crazy, but we're discussing a science where the vast majority of it is, we have no idea what it is. So this is a big mystery. But, again, while it's kind of frustrating, it's not surprising that there's weird stuff out there that's not on Earth. That's not weird. That we would expect that. It would be weird if everything outside of the Earth was just like stuff on the Earth. Yeah, we got it boring. All right, anyway, done. Now